Now, if you're already halfway through the problem and didn't notice you could factor an x out, that's okay. You could just do it at the end. Try it like this. Did any of you guys go ahead and just use this? Right? Did you guys see that? Or some of you guys lying? Did you guys use this for your quotient rule? It's okay if you did. It's okay. So I'll do it. Because you're going to have some weird simplification to do. Because look what happens if I kill an x, all of a sudden that 2 is going to disappear in its derivative. Right? So it becomes a lot easier. That's why simplification, yes. I'm going to do that if I can. I like it. That's right. You're not as good at that as I am.
Which one are you using? Are you using the one that's
I'm using this one. Yeah. That one will be easier. Let's see what happens with this one. The simplification should be a little bit weird, maybe. Stop there for a second. That's just applying the rule, right? So I haven't done anything yet. I'm just putting what the rule says would happen. And now we're going to see what happens. So the rule says derivative top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. Which again, it only makes sense because it would be to the negative 1, which would become negative 2, and that's why it makes sense the bottom is squared. So g prime equals 6x squared times this mess minus 2x cubed times, see, and that wouldn't be there if only, over this mess here. Yes?
So why is the bottom x cubed minus 2?
Oh, no. So I'm doing this not like that. I'm using this.
Oh, sorry.
That's my bad. Just because I felt like most of you probably did that, and I wanted to see what weirdness happens. Obviously, that would be easier. So let's see what happens this way. And what do I do next here? Can you guys see right now? Let's do this, or else I'm going to say. Can you guys see how many x's I can take out of here?
You can take out 2 after you.
Yeah, I can take 1 out from each.
Yeah.
So it ended with an x squared out here, right? Yeah. All right, you guys see that? Because there's 2 of them. And they each can give me an x. So that would become a 3, and that would go away. So it is x minus q minus 2. So then why did I do that? Because now that x squared can kill those 2 and 2 of those. Good. Maybe. So let's see. And so now I got 6x4 minus 12x minus 8x4 plus 4x all over x cubed minus 2 squared. Yeah, now you put your like terms together. So you're going to get negative 2x4 minus 8x all over this. Is that what you guys got? how I feel. Sure, Jeff. By the way, I know this shit really well, but I will make mistakes, so you feel free to call them out. Maybe don't get too much pleasure out of it. But I will totally make mistakes. I'll make stupid mistakes. I will totally will. And that's my proof that, yes, I bleed if you prick me. I am human. I think that one's all right. Look at it real quick. If I'll do it the other way, I'm going to do it semi-quickly. Let's just see if we get the same thing. So if I do it with the simplified form, it would be, I'm going to do it kind of quickly. All right? I'm going to get rid of the top, times the bottom. I'm going to go against my suggestion. I'm going to go ahead and do the derivatives at the same time. Minus the top times the derivative of the bottom. You can sort of see things happening all over the bottom squared. So I'll get 4x4 minus 8x minus 6x, got it, minus 6x4, yeah, there you go. All over, blah. So I get negative 2x4 minus 8x, so the same thing, yeah. Okay, good. Just notice, yeah, quicker. Yeah. So we'll get to the point where we learn the derivative of natural log, for example, and then the properties of natural logs will become useful. I can simplify using those before I attack it. So just to show you, just because we're talking about quotient rule, how could I simplify? Get out of there, man. We don't know what the derivative of this is yet. Some of you guys might, but just sit on it. Or don't. So if I had this, this would involve a quotient rule plus whatever the hell that guy needs, and it's a chain rule shit that we don't even know yet. But what can I do since it's a log?
Or rewrite it?
Yes.
X squared minus 1.
No.
Ln x squared.
Yes, ln at the top.
Minus
ln at the bottom. Because what are logs? No. Logarithms. They're exponents. So when you divide shit with exponents, what do you do with the exponents? You subtract them. Every property of logs is a property of powers. Because logs are powers. It's very simple to remember log properties. And this looks a lot easier. We can attack this with math, we just don't know the chain rule or what ln does yet, but it's a lot better looking than this was. Hell yeah. Alright. So I keep talking about it. Let's finally actually learn chain rule. And I found, I like this guy. Alright. Do I want to give this? Yeah, let's do this. Let me give you this. Give you this handout. I got a theorem in here that states what the chain rule is, but I'm going to prove it a slightly different looking way. Other way. Yeah, cool. A method to my madness. He thinks he doesn't speak too much. All right. So, what's up?
I got your quote.
Oh, well, there you go. Yeah, it sort of changes a little bit. So, I like this. We could totally take the derivative. Yes, we can. No, we can't. Not yet. Let me make that not yet. We could totally take the derivative of this all day long, right?
Yeah.
Totally. What is it?
2x.
2x. Easy. But we cannot take the derivative. We cannot take the derivative. But this, we can't. We can't. We cannot. You'd have to use limit definition let's not do that. In fact, we're going to use limit definition together, and then not on your own, don't worry, to prove the rule in general. So the main difference between these two is this part is easy, but over here, x squared plus 1 is inside. That's the whole point. So chain rule helps us when I have a more complicated function on the inside. And just to make sure you understand, it's not the radical's fault. If I have this, I can do that all day. Right? How do I rewrite that to be able to take its derivative?
X to 1/2.
What would y prime be?
1/2 x to the negative 1/2.
Alright, sweet. In stereo and all that kind of shit. Alright. But, and just to show you that squares is not always nice, we currently cannot do this. Unless we do what? Let me say it this way. We can't do that directly. We have to do a lot of algebra to it. We have to multiply, double foil in trouble. What's that? Sorry. Alright, I thought there was a suggestion. Anyway, so the whole idea, again, there's a function inside of another function. So if the inside, now here, I want you to understand, this is a function, x is a function, it's inside 10, but it's a linear function of x. Even more importantly, it's got a slope of 1. So what's really funny is once I show you the chain rule, I'm going to go back and show you that we actually have been doing it this whole time. Right? It sounded like a real cheesy part of the movie. You've had it inside you this whole time. Awesome. I'm going to click my heels together. I could have done that shit the whole time. Alright. That always bugged me. That was kind of evil. Click them heels together. I've had this since the beginning of the damn movie. Alright. I'll stop. Let's see. Oh. So, the most important thing on chain rule is understanding what the inside function is. And also understanding that there could be multiple insides, like Russian nesting dolls. That's where chain rule gets kind of evil, supposedly. Alright, so let me go through a little proof of chain rule. And I'm going to use the other version of the definition of limit, of derivative.
Yeah, explain it there.
So here's the function I want to look at. That is the very idea of a function that needs chain rule because it's a function that has a function inside of it, right? So let me use proof I do every day, so I've got it right here for myself. Let me use this guy. What would it look like if I used this, instead of h goes to 0, I'd use x goes to a. Who remembers what that looks like? F of x, g of x.
Minus f
All over
g of
x minus a. Cool. Now here is something, for the proof of the product rule, we had to add and subtract the same thing. For the proof of this, we're going to multiply and divide the same thing. Sure, Jeff. And this actually is almost too easy to believe. And there are some little things that people are, you got to be careful. And I'm like, screw you. That is never going to happen with the functions we look at. So a caveat here is, if you have an extremely weird-ass function, there might be parts of this that don't apply. Or no functions we would ever look at in any of our calculuses. 1, 2, or 3 here.
It goes like that, right, at certain points?
There are certain points where what I'm about to do won't necessarily hold.
Because we assume that it's...
Well, yeah, going in, we're going to assume that both of these functions are separately differentiable.
Oh.
So that's sort of like a given. And which means they're continuous everywhere that we want to look at. Especially around A. Right? Obviously, got to be around A. So this would be, what I'm going to do then is this. Which is kind of funny because some of you guys almost started to say this. I'm like, do you know this? So I multiplied and divided by the same thing. Right? And there is a little bit of stuff behind this, and it doesn't matter worth shit. It's fine. Right? Especially right now. Does that make sense so far? And just like earlier, can you identify what this piece is? Because it's the limit of this times that. So what's the limit of this?
That's the definition of the G prime.
G prime. Let me make sure you guys are with me. Yes, sir.
No. Is it okay because you just switched the denominators because they were multiplying? Is that fine when they're multiplying?
What happened? So what I did was this. And am I allowed to do that?
Yes.
Most of the time, yes. All the times that matter, yes. And then I just did this, yes. And that, of course, is totally 1/2 times 1/4 is the same as 1/4 times 1/2. It doesn't matter.
Okay.
Is that cool?
Yeah, no, makes sense.
All right. But I like that you're worried. There are some little things you got to be careful about, but there's such extravagant, exotic functions, and you don't hear the word exotic put together with function too often. But there are exotic functions. They're defined weirdly, and nothing you would actually ever run into. All right, that's the last I'm going to say that. This proof basically works. And then what the hell? Now, I really want you guys to understand. If g of x, if I looked at g of x as if it was just x, what is g of x? It's a number for any x, right? It's an input for f. So let me write it like this. If I looked at g as if it was u, I don't mean u. So u, let me see if I can say this really. Well, screw it, yeah. F of u minus f of b over u minus b. And as u goes to b. I really want you to get that. So look here, x, a. I'm circling the wrong thing. x, a, right? So the inputs are in the function, and the bottom are the inputs subtracted. So look, gx, ga, gx, ga.
So it's f prime of g of a.
Yes. So it's f prime of g, in this case of a. All right, now let me consolidate what we just figured out. And you don't necessarily have to, a lot of you guys are scribbling this down, so it's too late. I don't know if you're going to get much of them from that. So here's what we just figured out. And it's sort of like what they're saying. Well, yeah, this is what I got down here. So let me write it the same way I've got it down there. So the derivative of a function that has another function inside of it is the derivative of the outside function times the derivative of the inside function. So how is that a lot like product rule? Each of the functions gets its own term. Product rule, they're connected with a plus. Chain rule, now you see why it's called the chain rule, because that's a link. You link this guy's derivative with this guy. All right, let's try this out. Let's see what this looks like. And actually, let me do a couple examples that will show you why this is necessary. So for example, and I'm going to start with functions that I can do two ways, just to see that it makes sense, it works. And then we'll attack functions I can only really do one way. So let's say I had this function here. Let's start off with this. Let's do 2x plus 1 squared. Now obviously, before today, what would you do if I asked you to get this guy's derivative? What could you just do? FOIL it out. So you can say f of x. So one way to do it, we say, old way, would be, what do you get?
4x plus 4x.
All right, good. Everybody help me out. Thank you. And notice, people just do this automatically when I haven't taken a derivative yet, have I? No. And then people start plugging it in and think it's a slope. Don't do this to yourself. Don't be mean to yourself. The math is already hard enough. Now I take its derivative. What do I do? So just in case you didn't understand what I said earlier, that is the way I would do that problem. What I'm about to show you will work even if this was a 200, and then I do not wish to do it this way, right? I'm starting here. Why am I starting here? Just so I can see that I get the same answer both ways. So if I do it with this, the chain rule, new. Alright, so now I got it. Help me out. What's the inside function?
2x.
And what's the outside function?
Squared.
X squared kind of thing, right? So this is the important part. Derivative of something to the second power. What's that rule? It's that thing. Yeah, it's 2 times that thing to the first power. Then you link it. Now, right now, what's this? 4x plus 2. Is it the same thing?
No.
What's it missing? The factor 2. Well, thank God, the derivative of the inside is 2. Let me write this out like longer than you normally would. So it's the derivative of the outside function, treating this like it's x, it just comes for the ride, times the derivative of the inside. So that'll be 2 times 2x plus 1 times 2, which sure enough is 8x plus 4. Same thing. Right? Now, real quick, just on the heels of that, just in case, I know there's somebody out there going, why the shit would you do that? And I just said. So, let's do one that you would not want to do that way. Well, yeah, we do know sine's derivative, right?
Cosine.
Yeah, we've proven that. So if f of x is sine x, what's f prime? Cosine. We know that. We've proven it already. The next sections we're going to prove all the trig functions, or the main six. And I'm going to require you to memorize those. All right, because I'm a nice guy. Because how many guys got to go to 280? All right. And people that take my 280 and their teacher did not make them memorize certain things, I'm like, your teacher was mean. So don't think a teacher's mean when they make you memorize shit. They are a nice teacher. They are getting you ready for the next level. Anyway. So what if I had this? And I need to take that guy's derivative. What do you do first? The derivative of the outside function. So the derivative of sine of something is cosine of that thing
Times the derivative of the inside.
times the derivative of the inside. How am I going to rewrite this? Oh, I made it even. Ooh, I made it. Oh, you gotta have it.
Now you have to do it again. You have to do the
That's
second.
awesome. Yeah, I didn't even really mean to do that, but it's awesome. This is the, and some of you guys are like, what the hell are you people talking? To do this guy's derivative, what's going on here?
Another chain rule.
It's another chain rule. So this is that Russian nesting doll.
Nesting.
Is there a function inside of another function? Yes. And can you imagine, I could have went, sine of 4x. I could have just kept going. And what people do is they go too far with this. When do I stop? When the next chain doesn't have an inside function. Then I know I'm going to stop when it takes its derivative. I'll be done. Why do I know the next step is not? I'm not done once it because there's a function inside of a function. I've got to do the chain rule. So let's rewrite this. What's a better way to write square root of that?
So 1/2.
Yeah. All right. Cool. I like it. And that's better for derivatives because now I can apply. So what's that rule say now? The outside function. 1/2
5 minus 7x to the negative 1/2
times
the inside 7.
negative 7x prime. Let me just write the rule out. I will 5 minus 7x anyway. So it's the derivative of the outside function. Something to the 1/2 would have this happen. Times the derivative of the inside. Now I know I don't have to apply chain rule again.
Because it's not inside another.
Because there's no other inside function. This is just a nice linear function. It's awesome. There's nothing in the x, but it's just x there. Thank God.
No more nesting dolls.
So cosine of rad 5 minus 7x. Can we write this a little better?
That's 5 minus. Oh,
You put under
put on
2 over square root 5
Oh yeah.
times 7.
Times negative 7.
Negative 7.
Yeah, let me just throw that out here. Bop. Let me stop there for a second. Yes, sir.
So we have to learn this before we use U substitution? Or?
U sub is an integration technique. Anti-differentiation.
Can't you just do the same for this?
You can rewrite. Alright, so let me show you, just in case you have any trouble. I have seen this, but I personally don't think it really helps too much, but if it helps you, so...
Because it pulls it apart, right? You just
if I wrote this like, how would you even want to do this?
Sine of U.
Sine of u.
Just sine of u, okay?
And then you'd have to define
So
u.
u would be square root of 5 by 7x. So the derivative of this would be cosine u times u prime. So really, all this really does is then you can kind of do this separate and then throw it in. Alright, maybe. If you guys kind of see what this does for you, you can kind of separate your work. And if that helps you, okay. Personally, I never really saw, but it's not just about me. If this helps you out, great. So then you can figure out what's u prime going to be. Well, that's going to be, that guy prime. That's the derivative, and that's going to. Then you can call this M, this shit will just go insane. So once you have multiple nestings, this idea gets a little bit lost. That's why, personally, I try to get students used to just doing it straight out, so you can just attack the nesting next. What, do you care about this shit right now in this level? He's done. You're like, oh, good. You sit there. I totally focus on this dude next. Like it's his own problem. I say there's an inside function. Now I gotta, this guy's still there. Look at him. He's just there coming along. Okay, maybe. That kind of thing happened in your factory. You take a 2 out and the 2 just goes for the whole ride and you just focus on this shit, right? Same thing's gonna happen here. Alright, you guys try this one. Now that we know chain roll, we can do some cool shit. I won't hit that. I'll give you a decently not crazy one. That's not too bad. And I want you to realize, this is easy to not realize. If I took this function and did limit as h goes to 0, that whole thing, and somehow survived that process, I would end up there. And I'm not saying it's easy. That would be remarkably horrendous. So thank God we, in mathematics, stopped and we go, the next level would be this. No, let's go back and make some rules. That works always. And what we end up doing is, we apply rules within rules within rules, which is much easier than, holy shit, I don't even know if you can imagine what that would be like. That would be this. Oh, sorry. Holy shit. Sorry. Great job.
This is actually different, but for number 4 on like you try to find, is the outer function all of like 2 sine 5x squared?
No, the outer function is e to a power. And we don't know how to do e to a power yet. So
Oh, okay.
I don't know, I was being evil there. I don't know why I didn't. I forget when we learned that. Did we learn that already? I guess we learned it already. Here it is. No.
I do that higher.
I missed it. Here it is. Here it is. Okay. I got it. Blah, 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 blah. We'll have to do that next time. I got to backtrack and do E. Anyway, how do I rewrite this to do this?
2 minus x squared to the 1/3. 1/3.
1/3, good. So G prime.
1/3.
Good. 1/3 comes down in front of this.
2 minus x squared.
Negative 2/3.
Negative 2/3.
Times negative.
Yeah, let's just jump to the chase here.
Negative 2.
All right, so drew the inside, and then now just kind of collect stuff. This was negative 2x over 3 root. And you don't have to write it as a root, but you can if you want to. You can write it as a root. Root. Yes, ma'am.
So do we have to write it in the simplest form, or can we leave it as 1/3 times the common?
You know, this kind of thing has got to come out here.
Okay.
Yeah, I mean, I'm not going to necessarily take points off unless there's something that would have canceled or something, but you really should. Negative powers, that thing should flip.
Okay.
It really should happen. Yeah. And just as motivation for next time. Okay. I forgot when this happened, and it actually already happened. If I give you the function, in fact, let's just call this a to the x. Let's not be specific. Where a is greater than 1. If it was less than 1, it would look like that. Shit.
No, easy like
Dead purple. What's the slope back here approaching?
0.
0. So slope starts 0, and then what does the slope do up here? It gets larger and larger. So if I try to graph the slope is almost 0, but is it ever 0?
No.
It's always
Just
positive. What? So it's small positive, and then it gets bigger. So there's one exponential function whose derivative is itself.
Yeah.
Yeah.
Wait, but what does that mean?
That sounds like French. What's that?
So what does it mean if the derivative is the function itself?
All it means is it's the easiest derivative question ever.
So the
And it just means this. That's all it means. Like you have functions that are inverses of themselves, right? Like this function is its own inverse. You know what I'm saying? It doesn't mean anything amazing.
So like the derivative.
Yes. Cool. So next time we'll prove that.